Pedro Rato. I'm a Portuguese student of the University of Frankfurt, and I'm here at CERN for 2 years now. And I was already working with cloud before as an independent student. And I'm mainly researching the impact of charges and multiple charges in particle collisions. And I'm the person in charge for the data acquisition for this experiment. Cloud is a meteorology experiment here at CERN, and it's a collaboration of more than 12 institutes, international institutes. And our main two questions that we're trying to answer is, how does galactic cosmic rays impact cloud formation and aerosol nucleation in the atmosphere, and how trace gases and what trace gases are fundamental in the nucleation of aerosols in the atmosphere. So the main mechanism that we don't understand yet about the natural generation of clouds is aerosol nucleation. Aerosol are just liquid and solid particles that are floating in the air. We know that compounds like sulfuric acid and organics like isoprene and alpha-pinene are part of the nucleation of aerosols, but before cloud we didn't have a facility with low enough contamination and good enough instrumentation to actually measure this and understand these mechanisms. And so how cloud helps here is we created this chamber that we see here behind me. It's 27.3 cubic meters of stainless steel with very low contamination, and we are able to measure the gases that we put inside to parts per million and parts per billion of the compounds that we put in. So we have these gases that are directly injected into the chamber, and we put sulfuric acid in. We change the conditions of the chamber, for example, temperature, relative humidity, and we see how the gas will nucleate, will create these aerosol particles. And over the years, we have parameterized and discovered mechanisms for nucleation that we know are relevant in the atmosphere. The most recent one was isoprene, which is a gas very present in the Amazon, and a study that actually was a collaboration with also, besides all the other institutes, the Frankfurt University that did measurements in the Amazon troposphere, and they discovered the isoprene was present there, and we discovered that the isoprene nucleates. So it was a very important discovery. So one thing that's very known is ion-induced nucleation is a big part of nucleation. And how ions are generated, there are many processes, but one is, especially in the upper parts of the troposphere, galactic cosmic rays. Galactic cosmic rays is just a fancy way of saying any energy that comes from space. This is very dependent on solar activity. These galactic cosmic rays can be either generated by our sun or galaxies, black holes, anything that throws energy in our way will then hit the particles in the atmosphere and will ionize them. And this is very variant over time. And one of the things we try to understand is climate change. And so we want to basically see if there's a source here for the change in the climate and how impactful is this change. And the way we do it is we use the beam coming from the proton synchrotron here at CERN to ionize. It just comes from that hole there, and it hits the particles in the chamber. And we do different stages here in our usual runs. We call it neutral, GCR, and beam stages. So these are different stages of ionization of the particles inside the chamber. Neutral, we have electrodes inside the chamber that create an electric field that just clears out all charge in the chamber. And so we have no ionization basically being part of the nucleation that's happening. Then we have the GCR, where we just don't really touch what is ionizing in the chamber. This is just galactic cosmic rays that actually are hitting us right now. And these generate lower ion pairs per second. But then we have the beam that actually ionizes quite a lot. And so we have these 3 stages where we see how just the ions are impacting nucleation. And this can give a better understanding of how galactic cosmic rays and solar activity are also impacting our climate and the formation of clouds in general in the atmosphere. One thing that is very important to say is the only way the experiment has been so successful is because it's an international cooperation. And part of that international cooperation is modeling groups. So first we make the discovery of a gas being important in the nucleation. Then we try to parameterize it, see how different concentrations of the gas nucleate, how the temperature and relative humidity impact this nucleation. And once we have a parameterization of the nucleation from one gas, we give it to the modelers so that they can implement this into climate models and to predictions of nucleation in the atmosphere, because there's no clouds without aerosol nuclei for them to grow on. So we predict the aerosols, the mechanisms for going from aerosols to clouds are understood, and this is all incorporated into climate models. And it's a big effort for us to not just make discoveries, make them as practical and as useful as possible. And so it's very important to have this community inside our collaboration that has a direct communication with us, so that we also know how to guide the practical experiments, to give them the parameterizations they need to implement this into climate models and into predictions to be used in a day-to-day life. For such a heavy topic of climate change, and such an undiscovered topic as well, because even though we understand some mechanisms, there's a lot that we don't know. It's also a very juvenile and very exciting atmosphere that while we're doing experiments, because we are doing experiments that nobody knows the results. And so we will have 4 generations, literally from 20-year-olds to 7-year-olds in the control room, hands-on, doing the experiments and waiting for these lines that update every 30 seconds to tell us if what we're doing is revolutionary or another non-result, which both are equally important, because it's as important to find out that a gas is relevant as find out that a gas is not relevant. We have avid discussions with professors about the chemistry and what we're doing theoretically, as we have 3 a.m. during night shifts discovering that turns out this gas is also relevant in the atmosphere. So I just want to put that out, that cloud is a very serious, very successful experiment, but also it's a very good environment. And I feel it's not common in science to have as much fun as we have while we're having as important discoveries as we do. One of the main things that obviously climate change is the topic of is what's the impact of humans in the change in the climate, right? To know that, we have to compare how the atmosphere is evolving now to how it was before industrial times. So one thing that we know very well is before industry, what gases were in the atmosphere, because these gases get trapped in ice in Antarctica and stuff like this. So we know what the trace gases are from back then. But we didn't know, or we still don't know 100%, but we have a better picture now. We didn't know before cloud what these gases contribute to nucleation, what these gases are actually doing in forming clouds. And that's where cloud, the experiment, comes in. We are trying to understand, because for example, we know that human impact in the industrial times has increased the temperature by 0.8 degrees since 1750. We also increased the aerosol population, which creates more clouds, which actually contributes to cool down Earth. So where is the balance? Where is the positive? Where is the negative? And to understand that, and to also be able to understand how cloudy was the Earth before, because that also impacts the temperature, we have to understand how clouds are formed, how nucleation happens in the atmosphere, not just us making nucleation forcefully. And by understanding these mechanisms, cloud is helping to understand the impact of humans in the climate change. And as I mentioned before, galactic cosmic rays are also something that varies over time and depends on solar activity, which will have an impact on climate change. By understanding all these mechanisms that I've been talking about, we understand better climate change. We can predict better how the climate will evolve in the future and what was the impact of industry in the climate change. It's impossible, I'd say, to work with cloud and not become interested in the importance of all that we're doing and in the discoveries that we're making.